So we'll discuss now combination and silvering of lenses. Now, let's say we have a combination of lenses, which are, so we have few lenses which are at a negligible distance from each other. This distance is negligible. It's so less that we can assume that they're in contact. The object is placed at a distance of u from the first lens. So what is the image location? The medium is same. All the lenses are put in the same medium. So what is the position of the image? To find the position of the image, let's take one lens at a time. This lens. For this lens I can write u 1 by u plus 1 by v1 is equal to 1 by f1. Focal length of first lens. For the second lens, this becomes the object. Let's say it forms an image v1 here. So I can write minus 1 by v1, minus sign because to move from the object to the lens, I have to move in this direction. The ray of light moves in this direction. Plus 1 by v2 is equal to 1 by f2. For the third lens, I can write minus 1 by v2 plus 1 by v3 is equal to 1 by f3. For the fourth lens, I can write 1 by v3, 1 by v4 is equal to 1 by f4. So like this we continue till I get minus 1 by vn minus 1 plus 1 by v is equal to 1 by fn. Now if I add this, what do I get? This all gets cancelled. So I'll get 1 by u plus 1 by v is equal to summation of 1 by f. I varies from 1 to n. So what does this mean? It means that when we have a combination of lenses which are at a negligible distance from each other and the whole setup or the whole combination is put in a same medium, this medium is same, then to find the distance of the image, what we can do is we can find the net focal length of the combination. The net focal length of the combination is given by summation of 1 by fi is equal to 1 to n. This is when we have a combination of lenses. So what do I do? First, I'll find the net focal length of the whole combination and then I'll write 1 by u plus 1 by v is equal to 1 by f net. Now this formula or this approach is valid only when all the lenses are kept in the same medium. This medium is same for all the lenses. Now what happens when we silver one of the lenses? That means that what happens when we take a lens, let's say I take a convex lens and I silver one of its side. For this setup, I can write the equivalent focal length as, first time a refraction occurs here in this lens. So 1 by f lens. Now there is a reflection occurring. So 1 by f mirror plus again there is a refraction occurring. The second refraction occurs because the rays of light are reflected by the concave mirror. So again we have this term. This is because of the first refraction, this is because of the reflection, and this is because of the refraction again. So the net equivalent focal length is given by summation of these three. So this is when we silver one side of the lens. Now let's say we have a combination of lenses plus silvering of lens. That means we have something like this. Let's say it has a radius of curvature R1, R2, R3, and this one has R4. Okay, so what is the net focal length of this setup? This first lens has refraction twice. First time when the rays are coming, second time when the rays are reflected back. So I'll get 2 times the focal length of this one, first lens. Plus this one also has refraction twice, so 2 times 1 by f2. Plus this also has twice, 2 into 1 by f3. Plus this concave mirror has a focal length of 2 by r4. Okay, and now what is f1 or 1 by f1? 1 by f1 you know is mu 1 minus 1, where mu 1 is the refractive index of this medium with respect to the surrounding. 1 by r1 minus 1 by r2, and what is r2? R2 is negative, so this becomes 1 by r1 plus 1 by r2. What is f1 by f2? Is mu 2 minus 1, where mu 2 is the refractive index of this lens with respect to surrounding. Now this one is 1 by r2 minus 1 by r3. What is r2? R2 is negative. What is r3? R3 is positive. And what is 1 by f3? 1 by f3 I can write it as mu 3 minus 1. 1 by r3 minus 1 by r4. R4 is negative, so it becomes 1 by r3 plus 1 by r4 into mu 3 minus 1. So this is 1 by f3. Okay, so we'll put this here and we can find the equivalent focal length of the setup. Remember, when we are doing like this, we are considering each lens to be separately placed in this medium, because when we are writing mu, this mu is actually the refractive index of this lens with respect to the surrounding. That means we are assuming that each lens are separately put in the medium, and then we are getting this whole setup. So this is also again valid when the whole combination is placed in the same medium. Okay, now let's take an example before we close this topic. The example is as follows. Okay, the object is placed here at a distance of 100 centimeter. This radius is given as 10, this radius is given as 20, this radius is given as 30. Mu of this medium is given as 4 by 3, mu of this medium is given as 1.5. Okay, so the question is again very simple: find the location of the final image. So to find the location of the final image, I'll write the mirror formula, which is 1 by u plus 1 by v is equal to 1 by f, where f is equal to the net focal length. Here the medium is same, so I can use this approach. What is the net focal length? Let's write that: 1 by u plus 1 by v. This first lens has refraction occurring twice, once when there is the incident ray, and again second time when the rays get reflected from the concave mirror. So I'll write 2 times the focal length of this concave mirror. So it's 1.5 minus 1, 1 by r1. R1 is what? It's negative, minus 1 by r2. R2 is positive. Plus this again has refraction twice, so twice into 4 by 3 minus 1. 1 by r2 is positive, minus 1 by r3. R3 is what? Negative, because for radius of curvature in this is in this side, the rays are traveling in this side. So it's 1 by plus 1 by 30, plus the focal length of this mirror The focal length of this mirror is 2 by the radius of curvature, which is 30. So this is my equation. If you solve this equation, you will get V. Now this equation is completely mathematical, so I'll leave this up to you to solve this now. So we are done with this topic of refraction in spherical surfaces. So we'll wind up this topic. The topics left now are optical instruments, dispersion, aberration, etc. So we'll discuss this in subsequent chapters. Thank you.